Okie doke. So we are into section 13.4, which is on splitting fields and algebraic closures. And before I get into that too much, I'll just say a word about the section we're skipping, all right? I've tried not to write too much, I'll just try to talk, but in section 13.3 of Dummett and Foote, what do they cover? They cover, classical geometric constructions, all right? Classical straight edge and compass constructions. And to summarize the section, what that section shows is that if you study how to construct numbers using a compass and a straight edge, that the numbers that you can construct correspond to degree 2 extensions. So basically, an extension, numbers that you can construct from straight edge compass constructions of a given set of numbers corresponds to extending that given set of numbers, and that set of numbers is like a subset of the real numbers. It corresponds to extending that given set of numbers by an extension of degree 2 to the power k for some k. So you could have a degree 2, a degree 4, a degree 8, a degree 16 extension, but you can't have a degree 3 extension or a degree 9 extension or a degree 5 extension from using straight edge compass constructions.
So, like, are you assigning numbers to number of lines in a geometric pattern?
You're assigning a token line to be a distance to be 1, and building. It's described in section 13.3. I can't get into it without getting into it. But yes, there is a method using compasses and straight edge to construct numbers. There's three problems that have been famous since ancient times in constructive geometry. That's the problem of doubling the cube, taking a unit cube and constructing, using straight edge compass kind of constructions, a cube that has distance 2, like length 2 on, or excuse me, am I saying this right? Curses. I feel like I'm saying it wrong. So is it possible, here I'll just read them. Is it possible using only straight edge and compass to construct a cube with precisely twice the volume of a given cube, right? So can you double the volume of a cube using straight edge compass constructions? Is it possible using only straight edge and compass to trisect a given angle, theta? Is it possible using only straight edge and compass to construct a square whose area is precisely the area of a given circle? All right, squaring the circle. And the answer to all three of these questions is no, because if you study them, you can show, if you study them, you can show that all of these things correspond to, well, the circle one corresponds to an infinite extension, so it's not a degree 2 to the whatever power. But the doubling the cube and the trisecting the angle correspond to, I believe, order 3 extensions. The details are given in section 13.3, and since they're order 3, they're degree 3 over the base field that you're extending, subset of real numbers you're extending. They cannot be straight edge compass constructions. Although there are specific angles that you can trisect, but it has to be like a quirk of the angle you're using. But generally you can't. So, like I think if you have 3 degrees, you can trisect that. But anyway, so 13.3 is interesting, but really kind of off the beaten track for us. So I've said what I've said. So let's see here. Definition. Extension field K of F is called splitting field, a splitting field. of f, right, of x, rather of f of x and f, big F of x, all right, if f of x factors into linear factors in k of x, right? And f of x does not factor completely into linear factors over any proper subfield of k containing f. I'll say it this way, f of x is not split in any subfield of k containing f. So split is a nice term. To say the polynomial is split is what we mean when I say factors into linear factors. That's split.
Essentially, because if you had infinite factors,
So it's something like this, right? Like x minus r1, x minus r2, x minus rn for some a. Well, I think actually a has to be in. I guess a has to be in f the way I've set it up here. But of course, the r1, rn could be in k, yeah. Let's see here. So, example, we could look at f of x equal to x squared minus 2 in, let's say, q of x, right? What's the splitting field? Well, it's definitely the case that f of x is equal to, right, x minus square root of 2 times x plus square root of 2, right? Yeah. And in r of x, right, I mean, definitely, if we look at the real numbers, we can factor it, it's split, right? But that would not be the real numbers are not the splitting field because they're needlessly big, right? Because this, you could replace this with what? With just q adjoin the square root of 2, right? So the splitting field here is q adjoin the square root of 2. This is splitting field. For, x squared minus 2 in q of x.
So, well, our definition talk about having, like, how big the k can be.
It does. F of x is not split in any subfield of k containing f. See,
Okay.
if I tried k equals r, it doesn't work because q adjoins square root of 2 is a proper subfield of r, which splits f of x. So just to give a big picture snapshot of what this section says, this section says that basically there is a splitting field for any polynomial, and it is unique up to isomorphism, all right? And of course, we know, like, more than that. The other major thing this section does that I will not do in class is it says, okay, so if you have a polynomial with rational coefficients, right? You know full well that that will factor completely, that splits in the complex numbers. Because the complex numbers, not just that, but any rational polynomial is split over the complex numbers. So any splitting field I find for a given rational polynomial is a proper subfield of the complex number system, right? So that complex number system for rational polynomials, it has all possible splitting fields for all possible polynomials, right?
Yeah.
And so what he describes in this section also is a way to do something similar for an abstract field, like the proposition 30, I believe. It says, for any field F, there exists an algebraically closed field K containing F. Proposition 30. I'll say that again. For any field F, there exists an algebraically closed field K containing F. I'll just say proposition 30. Now, we haven't defined algebraically closed yet, have we? Not in class, at least.
Oh, yeah, we used that homework problem.
Right. So, theoretically, what this is saying is that there's an analog of the complex numbers for any field. Okay? You give me a field, you can find an algebraically closed extension of that field in which all of the polynomials in the given field are split.
Can you define analog for me? Like, is that like?
Well, what I'm saying is this any field
No,
could.
I get what, just like the word.
Oh, analog, like similar but different.
Okay.
Is what I mean by that. But I mean similar but not necessarily the same. I'm saying it's like the complex number system, but so proposition 30. I mean, we don't really need it because most of our examples are rational polynomials, right? So we know.
Yeah.
Push comes to shove, we can try to do the math and the complex over like complex factoring, and we can look at the complex factoring and see the answer to questions.
Yeah. Well, I
You know?
because Q joined I splits x squared minus 2, or x squared plus 2, sorry.
Mhm.
But it's a subfield of the complex numbers.
Right. But well, anyway, but the proof of this proposition 30, it involves some pretty heavy hitting stuff. A really clever argument due to a mathematician named Artin and Zorn's lemma and such. All right, so actually, let me just jump the shark here a bit. Well, let me just try to get the theorems out of the way, and then so theorem 25. Yeah, I'll go back to start. For any, that's the end of the end of the section. For any f of x over a field, right? A polynomial with field coefficients. There exists an extension k over f, which is a splitting field. For f of x. Theorem 25. All right. The proof of that is by induction on degree. So, but anyway, definition. So, K is algebraic extension of f, which is splitting field over f I'm just going to say splits collection polynomials f of x in then K is called normal extension. But he said we usually use the term splitting field rather than normal expression, normal extension. Let's see here. I don't like his wording here for a collection of polynomials f of x. It's a normal extension of f. I guess he means, well, well, he means what he means. So I think it could be more like, maybe it splits two polynomials, right? That would be a normal extension. And we'd still, I think he was trying to say is it's still called a splitting field if it splits two polynomials, you know. But then, well, anyway. I don't really have anything to say there, so let me stop saying things. Find a better piece of chalk, maybe. Okay, so proposition 26.
Okay.
I'm okay. Can't say the same for the chair. Let's see here. Proposition 26. A splitting field for poly f of x with the degree of f of x equals to n, right? So a splitting field for an nth degree polynomial over f is degree at most n factorial over f. Now, the proof of this, I think, is worth looking at. I mean, the proof of every theorem in Dummett and Foote is worth looking at, but as you know, until we can shadow clone ourselves and like give multiple lectures at the same time, we can't do all the proofs. So, what's that?
But it's a debt prop.
Oh, it's a proposition. Let's see here. So the proof is actually before the proposition, essentially. So here's the proof sketch. So you got f of x, right? Degree n, right? Right. And suppose you adjoin a root to f, right? Alpha in f1 over f with f of alpha equals to 0, right? We know we can do that by the theorems of the previous sections, right? You can always find an extension in which we have a root. And so that then gives us the following. F of x is equal to, well, x minus alpha times, let's say, f1 of x, right? This is in where? This is going on in f1 of x, right? This factoring is happening in the extension, right?
Yeah.
Because the alpha is in f1, all right? right? Well, but f, yeah, I mean, well, yeah, excuse me. The degree of f1 is what?
F1 of x
Yeah,
would be n minus 1.
n minus 1, right? But then, and so,
Oh, you can keep doing that with F1. Yeah, gotcha.
So-
That's where you get the factorial.
yeah, so I guess the thing I've buried so far, though, is what is the possible degree of, what's the possible degree of f1 over f? Since we're adjoining a 0 of an nth degree polynomial, well, you know the song and you know the story. If that polynomial is irreducible,
Yeah.
that's a degree n extension.
Yeah.
So that could be n degree, if f of x is irreducible, then, then we have f1 over f is anyway, it's less than or equal to n. That much we can say, right? Where equality is met only if, in fact, f of x is irreducible. Okay? And, I mean, f1 could be equal to f if f of x factors,
Yeah.
right? Okay. But anyway, that gives us a cofactor of degree n minus 1, right? But then, using the same theorem, we can find a 0 of that, right? So then, let f2 over f1 have, let's say, beta in f2, right? Such that f1 of beta equals to 0. And so, f1 of x, well, f1 of x is equal to what? X minus beta times f2 of x, yeah? And so we got altogether f of x equals to x minus alpha, x minus beta, f2 of x, yeah? But you notice that the degree of f1 is n minus 1, right? So we have the degree of f2 over f1 is less than or equal to n minus 1. And we just continue doing this argument. Extend, 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 extend. We can only do this n times, right? Because eventually you have n factors. And each time, the extension has one less degree than the time before. So eventually you get to x minus alpha 1, x minus alpha 2, x minus alpha n, right? And that is in, fn, which is over fn minus 1, which is over over, f1, which is over f. And, the degree of fn over f is less than or equal to then n times n minus 1, 3 times 2 times 1, right? Otherwise known as n factorial. So what's this say? This says that a splitting field for a polynomial f of x of degree n has degree at most n factorial over n.
You can also say that with that one thing, fn over f, you split up into fn minus 1 over f. No, fn minus 1 over fn minus 2 times fn minus 2 and fn minus 3. Like, keep that line of logic. Because every degree would be one less than the other, and you also get the factorial.
Oh, right, yes, that's where this is coming from, exactly. It's that, yes.
fn over f is equal to fn over fn.
Yeah, it's right, it's this thing. If we have fn F1, n minus 1, F2 over F1 over F. If we have this tower of fields,
Yeah.
then the degree of F n over F, as you say, is equal to the degree of Fn over Fn minus 1 times the degree of Fn minus 1 over Fn minus 2, dot, 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 dot. Eventually we get to F1 over F, right? And then that is straight up less than or equal to 1 times 2 times 3, dot, 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 times n, which is, of course, n factorial. I mean, yeah, that's exactly it. But we know that many cases, we're not going to need an n factorial extension. For example, if your polynomial is already split in the base field, you're done. Like a base, then in base field this is the splitting field. All right. So I'm trying to do today is get all the theorems out in front of us and then dig into the examples. So that will make the theorems come to life, yeah. So where was I? Goodness gracious. Theorem 27, I don't want to write down, but what it says is that if you have a splitting field, well, it says if you've got an isomorphism of fields, right? And if you look at a polynomial over the original field, right? And then you look at the image of that polynomial under the isomorphism, right? Then the splitting field for the original polynomial will be isomorphic to the splitting field of the isomorphic polynomial. So there's a natural transference of splitting fields under isomorphism.
Have a field, go to another field. If I split this field also has a thing that can be split.
But splitting is always with respect to a polynomial. So this field is split for f of x.
Yeah.
Means
whatever it maps to.
the map to f of x is also split over here for an isomorphic, and the fields in which they're splitting are isomorphic. That's theorem 27. And one of the things that says then is that implies then also that the splitting field for a given polynomial is unique up to isomorphism, because you can take the identity map on the from the field to itself. So if you had two different splitting fields, then the identity map will then lift to an isomorphism between the splitting fields for that given field. But I know I'm being slightly fuzzy, but let's see here. It is laid out in detail on page 541 to 542. So the yeah, I mean here's core. I mean I'll write down the conclusion for posterity. Any two splitting fields of a polynomial right are isomorphic. Now, definition. The field F bar is called an algebraic closure of F if F bar is algebraic over F and if every polynomial f of x in big F of x splits completely over F bar. Right. So that F bar can be said to contain all the algebraic elements over F. So F bar contains all algebraic elements over F. As we talked about on the phone, one of your homework problems basically says that the first sentence in this definition implies the second. So what does it mean for, what does this mean, F bar algebraically closed over F? What was our definition of that? Like this, what's that mean? That means that if f of x, right, is an element, a polynomial in F, right? That's not what it means. Oh, curses. What was our definition of algebraic over F? I think it means for each alpha in F bar, there exists F, that's not right. Oh, goodness gracious, all of a sudden I've forgotten the definition of algebraic. Sorry. Very aggravating. I probably should be looking in the section titled Algebraic Extensions, huh?
Alpha is algebraic.
Yeah, alpha's.
Over F, if and only if F of alpha over F is fine, right?
No, it says the definition is that an element is said to be algebraic over F if alpha is the root of some non-zero polynomial in F. And then the extension k over F is said to be algebraic if every element of k is algebraic over F. So it was what I was about to write down, and I just couldn't bring myself to do it, which was that if alpha is an element of F bar, then there exists F of x in F of x such that F of alpha equal to 0. So an algebraic extension is one for which everything in the algebraic extension appears as the 0 of some polynomial in F. All right.
Okay, so I'm just going to restate that. So alpha is algebraic over F if it's a 0 for a polynomial in F.
Mm-hmm.
And for a field to be algebraic over another field, that means every element in that field has to be algebraic.
Exactly. So I've stated that here in yellow. You know, if alpha is an F bar, then there exists F of x in F of x such that F of alpha is 0. Yeah. Now, at the danger of working your homework, actually, I'm not too worried. If every polynomial F of x splits completely, well, okay, so, oh, I see. There's a slight thing here, right? So, so give a polynomial, right? F of x. If it's constant, there's nothing to do. All right. If it's linear, we're done. If it's quadratic, then the question is, well, if it's quadratic and it splits, we're done. If it's quadratic and it's irreducible,
You got an element.
then let's see here. I'm still not getting at it.
Are you talking about what you found?
I'm talking about why it is that, f bar being an algebraic closure of f implies that, f of x can be written as a times x minus, alpha 1 times x minus alpha 2, x minus alpha n for alpha 1, alpha 2, alpha n in f bar. Like, why is it that f bar being algebraic over f implies that any polynomial in f can be written this way?
Well, for it to be algebraic, for the field to be algebraic over it, you already have to imply that these are zeros. Like every element's a zero. Like alpha 1 is a zero, alpha 2 is a zero, alpha n is a zero.
Yeah.
And so when you put all those zeros together, you get that f of x. If you put all those factors together, you immediately get a polynomial that splits completely over the field.
Yeah, but I'm just writing that formula down. Like, why do we get to write that formula? So like,
Still, because every algebraic element that we labeled alpha 1 to alpha n, you can still put those together.
how about, all right, so how about this? We know that there exists a splitting field for the polynomial, right? Mm-hmm. So we know that there exists a splitting field. Whoa. Let's put, instead of assuming f, let's replace this temporarily with k, the splitting field. Mm-hmm. Right?
Yeah.
Okay. Then the question is, okay, where are these alphas? I mean, what can you say about the alphas? Well, you can say this, right? F, like you,
They're all algebraic.
yeah, I mean, f, we have this f of alpha 1, right,
Mm-hmm.
is equal to 0, right? But f of x by assumption is in here, right? Mm-hmm. So that tells me that alpha 1 is in f bar because it's algebraic over f. So I think what you're saying is what I'm saying. It's just like the reason we have this formula is that there's a splitting field.
Yeah.
And then the reason that the zeros in this formula have to be in the algebraic closure is because they're algebraic by this formula. I mean, it says that these are zeros of that polynomial, therefore they're algebraic. Consequently, I can't say that, let's see here, how can I say this? I'm not saying that the splitting field is equal to f bar. What I am saying is that the splitting field has to be a subset of f bar. Right, so but that doesn't really matter. I'm observation. It's not part of the theorem, right? But observation, the splitting field is a subset of the algebraic closure. And like the example we already saw, right? Like the algebraic closure of the rational numbers is bigger than the splitting field of the rational numbers with respect to x squared minus 2. All right, anyway. So there's this, and then what was the other definition that was plaguing us?
A field K is said to be algebraically closed if every polynomial with coefficients in K has root in K.
Right, so can I erase? I'm going to erase this. I'm gonna. All right. Well,
Just erase.
I erased this one. Well. Eh. Okay, I'm gonna erase this. I don't think we need these. Definition. Field K is algebraically closed if every polynomial has a root in K. By the way, so that definition straightway leads to the fact that every polynomial in F is completely split. Because if it has a root, then you can factor that x minus the root out, which then leaves you another polynomial in K of degree n minus 1, which also has to have a root, which then leaves you another polynomial of degree n minus 2, which also has the root, and so on and so forth. Right. So, so he says, read paragraph here. He said, it is not obvious that algebraically closed fields exist, nor that there exists an algebraic closure of a given field F. Note that if K is algebraically closed, then in fact every f of x has all of its roots in K by the argument I just outlined. All right, so it has to be split completely. Hence, K is algebraically closed. No, excuse me, hence, if K is algebraically closed, then K itself is an algebraic closure of K. And the converse is obvious, so that K is equal to K bar, if and only if K is algebraically closed. So observation, K algebraically closed, if and only if K bar is equal to K. This is cute notation because, by the way, like the closure of a set in complex analysis, like we were talking about earlier, the set is closed if and only if it's equal to its closure. It says algebraically closed. Yeah, it's closure. Yeah. So yeah, fun. And so he says, proposition 29, let F bar be an algebraic closure of F, then F bar is algebraically closed. All right, so proposition 29, F bar is algebraically closed. All right, great. I mean, what did it say? It said every f of x, every, you know. So if you take, like, what do? You take f of x in f bar of x, what happens?
See, that's one thing I don't get. Why can you, okay, maybe I'm reading this wrong. Let me make sure.
Take your time.
Okay, so F bar has all the elements that split F.
Mm-hmm.
But what if there's a polynomial in F bar of X that doesn't split? That's irreducible.
All right, well, let's see here.
Because then you have to have like f or prime.
See your proposition. Give me a second here. Right. Well, let's see why that's. Let's try to understand why that doesn't happen, right? So he begins the proof by let f of x be a polynomial and f bar of x, right? And let alpha be a root of f of x. Right? So f of alpha equal to 0, right? Then what? He says, then alpha generates an algebraic extension f bar alpha of f, right? F bar alpha is an extension over f bar, right?
Yeah.
But the thing is, f bar is as we've discussed before, algebraic over f.
Yeah.
So this is over f, right?
Oh, and you're saying that if it splits f, it has to be back in f bar?
So this, what I'm saying is this implies alpha algebraic over f.
Oh, and f bar is a set of all algebraic elements.
Right,
Over,
so therefore alpha must in fact be in f bar.
my question was answered by the proof.
Uh-huh, that's what proofs should do. Now, that's proposition 29. Proposition 30, I already wrote, right? That I'll say it again. For any field f, there exists an algebraically closed field containing f. Proposition 31. Let K be an algebraically closed field, and F a subfield of K. Then what? Then F bar, then the collection of elements of F bar of K that are algebraic of F, algebraic over F, is an algebraic closure of F. The collection of elements of f bar of K that are algebraic over f is an algebraic closure of f. An algebraic closure of f is unique up to isomorphism. So, in other words, this basic. Let me just kind of put it into words. What this is saying, ... is that you can say f bar is a subset of K. Right? So like, if your field is a subfield of an algebraically closed field, right? And then you take the algebraic closure of that subfield, then those are going to fit inside the algebraically closed field. Okay. Man, I can't fight the feeling like I'm not saying anything here. I know it's never the case, right? The fault is mine. I could just, the collection of elements f bar of K that are algebraic over f is an algebraic closure of f. An algebraic closure of f is unique up to isomorphism. And then fundamental theorem of algebra, the field of complex numbers is algebraically closed. Right? Maybe corollary 32 will help us bring more light to proposition 31. What's corollary 32 say? Maybe that's what I need to see in order to understand proposition. Corollary 32 says the field of complex numbers, right, contains the algebraic. I think I need examples to understand that proposition we just went through. contains algebraic closure for any of its subfields. So, in particular, Q bar is what? This is the collection of complex numbers that are algebraic over Q. Okay. That is not equal to C. That's the thing I'm struggling with. It's not C itself. It's smaller.
See, that's what I don't get. Well, maybe it's because you can't factor like E or pi.
Exactly. Exactly. Pi is not algebraic over Q.
Yeah.
That's exactly it. But on the other hand, on the other side of things, the algebraic closure of the real numbers, that's the complex numbers.
Yeah.
Once you join I, you've got the whole deal.
Yeah.
Another one of your homework problems. So.
That's the only thing I was just like, well, I guess you can't throw in these random things.
Let's see here. So, I don't know where I've been panning before I start erasing everything. If it's not already too late. Sorry. All right, well, let's see if we can appreciate the theorems with some examples now, yeah? So, start out simple. X squared minus 2 has Q adjoint square root of 2, isomorphic. In fact, equal to Q adjoint minus the square root of 2, right? Those are splitting fields. I mean, I'm just saying adjoining square root of 2 or squaring minus square root of 2, same field actually. That's the splitting field, right? 2, if we have x squared minus 2 times x squared minus 3, all right, we're dealing with it as a rational polynomial, then the splitting field is Q adjoin square root of 2 comma square root of 3, right?
Isn't it also 6, square root of 6?
That is not, no. There are 3 proper subfields of this.
Yeah, they have a picture of it.
Right, so the picture is this. It has this one. It has this one. It has that one. And these are all proper subfields of the splitting field. And these guys, of course, are all extensions of Q. And I believe they're each degree 2.
Okay, so they're isomorphic to each other?
Yeah. Well, are these isomorphic to each other?
Because if they're subfields, they can't be. That means they don't contend.
Well, these are not splitting fields, but I do think they're isomorphic because they're all
Degree 2?
they're degree 2. I'm not sure they're isomorphic.
I don't think so, because what do you map to root 2 and what do you map to root 3?
Very good. They're not isomorphic because you cannot find a root 2 over here,
Yeah.
and you cannot find a root 3 over there, and you can't, yeah. And there's no way to get root 2 or root 3 from root 6, which is also the problem with making this equal to that, because this has root 2 and root 3 in it, so it can't be this. Because there's no way to get square root of 2 or square root of 3 just with like a sum, difference, or product, or quotient of root 6s. But there it is, the splitting field. And in terms of degree, check it out, right? This is a quartic polynomial, right? Quartic.
Yeah, 'cause
And you can prove that this does not split in any subfield of this, right? So this is the smallest you can get.
Yeah.
You can make it bigger, right? You could extend this all the way to the real numbers.
Yeah, but you only get 2, 6, or 3. What do we just said?
Right. So what I'm saying is, like, this is as small as it can get to split that polynomial, right?
Yeah.
What degree extension is this? This is a degree 4 extension. It's also called a biquadratic extension. 2 times 2 is 4. And so in principle, it's a quartic, right? So it could have had a splitting field of degree 4 factorial over Q, which would have been 24. But in fact, we could make do with just 4. But this one did need the degree 2 extension, which is 2 factorial. The next example we have also looked at before, but it's worth talking about again. Remember, we looked at x cubed minus 2, this polynomial. And we saw that this has zeros of the cube root of 2, and then the complex roots, cube root of 2 times minus 1 plus I root 3 over 2, and cube root of 2 minus 1 minus I root 3 over 2. You know they have to come in a conjugate pair. It is, after all, a real polynomial. So these are the roots of x. So if I call this alpha 1, if I call this alpha 2, if I call this alpha 3, of course we can write x cubed minus 2 as x minus alpha 1, x minus alpha 2, x minus alpha 3, right? But it's certainly not the case that q adjoin the cube root of 2 is not equal to q adjoin alpha 2, right? I mean, this is real. This is complex. So they're not the same extension field by any sense, by any stretch of the imagination, right? And the question then is, what is the splitting field here, right? So the splitting field is basically what you're looking for is the smallest field which contains all the zeros of the polynomial, right?
Yeah. So would you just join? Well, we know that alpha 2 and alpha 3 are. Ooh, no, we don't.
So yeah, here's the
Negative.
so here's the trick. If you look at the quotient of alpha 2 by alpha 3, what happens?
You get rid of a 2, and then you get conjugate over like you get.
Right.
Yeah, you get minus 1 plus I root 3 over minus 1 minus I root 3.
Right.
Or vice versa.
Exactly. You get that. And cleaning that up a bit, what do we got?
You get like 4 on the top, and then you get like some complex number.
So yeah, you said it got a 4. I get 1
You
minus.
don't get a 4. You get a 4 on the bottom.
I get 1 minus 3. I get minus 2, right?
Yeah.
The conjugates
2
cancel, right?
Yeah, minus.
Or they don't cancel,
No, they cancel on the bottom.
but they.
You get 4 on the bottom.
So we get 4 on the bottom,
Yeah.
and we get what?
Minus 2i 3, I think.
Yeah, minus 2I root 3, right?
And then minus 3. Minus 3. Yeah.
I already did that in the minus 2.
Oh, okay.
1
Yeah.
minus 3 is minus 2.
Okay, yeah.
So the point here, though, right, is just that you've got like minus a half, right?
Yeah.
Minus a half times I, times the square